My name is Kamil Dudka, and I will talk about fully automated static analysis of Fedora packages. Fully automated here means that we have a tool that takes a source RPM package on its input and returns a list of bugs in the package, or more likely possible bugs in the package which we still need to check manually. I will first say what static analysis in this presentation means. Then I will go through the static analysis tools we have in Fedora and describe how to use them, what problems we can face when analyzing RPM packages. And finally, I will introduce the tool for the fully automated static analysis of the RPM packages. Here is the generic definition of static analysis, which is an analysis of code without executing it. This is of course too much generic, and it covers more than we need in this presentation, because static analysis is also used in compilers and in auto-completion hooks in your editor, for example. In the context of this presentation, we are focused on static analysis as a means of finding bugs in software and especially in RPM packages. So I have covered the definition of static analysis. Now I will go through the static analyzers we have in Fedora and we can use. As I said, static analysis is also used by compilers, and GCC is the primary compiler used for compiling C and C++ Fedora packages. Besides it compiles the code, it also produces various kinds of useful warnings. There are some problems with these warnings and processing them, which I will cover later. But I would place GCC on the list of analyzers we have, static analyzers we have in Fedora, because of these warnings. I forgot to mention that there is enough room for discussion in this presentation, so if you have some questions, feel free to stop me at any point. Then we have some analyzers that are ready to handle various, vast majority of Fedora packages, and currently we use CTP check and CLang. Maybe there are some more analyzers we don't know of, so feel free to suggest new ones. CTP check is a simple static analysis tool based on pattern matching, and CLang is provides a set of static analysis checkers built on top of LLVM, which is low-level virtual machine infrastructure. Then we have some analyzers with limited scope of use, as for example Sparse, which is mainly used by kernel developers. It can handle only the C language. It can of course be applied on more packages, but if you, for example, read the upstream mailing list, most of the input really comes from kernel developers. So it is likely that there will be some bugs. You will encounter some bugs if you try to apply it on some other software. And finally, there are some research prototypes which come with limited level of automation, as for example Pharmacy, which uses some obscure parser of the C code, which basically works, but there is a big chance that the parser will understand your code differently than the compiler we use for compiling the packages.
This S patch also, which Kamil uses.
S patch? Yes, thanks for the suggestion. We are definitely looking for some other analyzers we can plug into our tool. I will talk about this later, so feel free to propose it on our mailing list and we can write some plugins to cover this tool. Basically, the problem with other analyzers is that they work well for some project, but they are not ready to be applied on any given RPM package. So there is a lot of work between analyzing few packages and being able to analyze any given package. So
I don't think with any analyzer you would be able to analyze all the packages, because a lot of analyzers are language specific. Like
yes, I forgot to tell that for now we analyze only C and C++ packages. Yeah. So that's the current limitation. And in this area, CPP check and CLang are really great. Yeah. And if they fail, we are able to handle it and provide the partial results they give us. So here is some details about GCC warnings. As I said, some of them are quite useful. They usually point to real bugs. And they are taken seriously by upstream developers. In, I believe, most of the projects we package. But they are usually ignored by Fedora package maintainers. Basically, whatever can build fine does not need any fixing. So there was some effort to force build failures by treating some warnings as errors. So if the maintainer does not fix it, he is not able to build the package. But by forcing people to fix code, which does not necessarily contain bugs, we can introduce new bugs. So forcing people to fix all occurrences of some kind of warning is usually a bad idea. I think the correct approach is to provide the maintainers with some equipment, with some efficient tools for processing warnings, such that they will love to fix the warnings. And we have such equipment. I will advertise it later on. The problem with GCC warnings is that they are difficult to process. If we look only to build logs, they can be messed up because of building in parallel, building packages in parallel. They use the diagnostic messages of GCC use relative paths with some build system, so they are ambiguous sometimes. We can have the same base name in multiple directories, so we would like to use absolute path. And the format of GCC is not parser friendly. For example, if there is a multi-line warning, you cannot just use tools like diff or grep to, for example, check whether you are introducing new GCC warnings in a new version of your package. The second major enough static analyzer was CPP check, which is based on pattern matching. That's a very lightweight static analysis. We cannot expect much, but it still provides quite useful results. There are basically two choices how to run CPP check. The first one is easy. We just give it a directory with sources and run CPP check on it, without actually telling CPP check how the source codes are supposed to be built. So it is not very precise. And the second mode is that we can run CPP check similarly as a compiler for each single unit and give it the correct preprocessor flags. So in the first mode, the problem is that CPP check does not know how to preprocess the sources. There can be some missing include files which are ignored. It has to try various combination of the defines used in the code. It, for example, can report bugs in code that is not going to run because it's, for example, specific for some platform. And there is basically no estimation about the time we need for the analysis, because there is no limit and it runs on all the sources, it tries all combination, so we can wait too long. For the second mode, as I said, it is much more precise because we tell CPP check how to actually compile the code, but doing it generally for RPM packages is not so trivial. Therefore, we wrote a new package exactly for this, which allows to hook CPP check on the compiler fully transparently. So we just insert a directory into our path such that the wrapper is called instead of the compiler, and the compiler takes care of running both the compiler and CPP check and provides the results as if the messages were produced by GCC. So it's now in Fedora, you can try it and report some feedback. Do you have any questions to CPP check or its use? Not yet. The second one is C-Lang analyzer, which is based on data flow analysis. So it is more mature and provides deeper results than compared to CPP check. It does not support the mode of CPP check to run it just on sources. We really need to be able to compile the code. So we need to tell C-Lang how to compile it. And for this purpose, C-Lang provides a Perl script named scanbuild, which takes care of all of this. So it provides its own compiler wrapper, which runs C-Lang transparently to the compiler and gives us the result. For example, you can just write RPM build command by this wrapper and get the result. The results are provided in HTML or PRIST format, which is quite different from both what CPP check and GCC produce. So we have yet another format for representing the results. And other problem is that this scanbuild script is known to fail for various packages. For example, for Kerberos, it does not use the wrapper at all because the spec file overrides the CC variable. So by running this command, you actually get no result. Similarly, Pidgin uses some buggy version of libtool, which does not recognize the wrapper as a compiler. So it not only that we don't get the results, it also breaks the build in this case. Question?
Yeah, I just don't understand that command line right there. What is being analyzed?
This command.
Yeah, so scan build is the thing provided by Clang. Are you analyzing RPM build or the RPM?
Basically, this command builds the package.
Right. Okay.
And if we press it by scan build, it installs the compiler wrapper such that each single compilation unit compiled during the build is analyzed. So it takes slightly more time, and finally it collects the results and represents it in the format we choose.
Okay,
Does that answer the question?
Yes.
Thanks for the question. So we can take these bugs as packaging bugs, but users usually don't care. If they are able to build the package, they want us to be able to statically analyze the package. So it would be good if we have some tool that can work around these bugs. So to sum up, we have mature enough static analyzers in Fedora that can be used to analyze our packages. The problem is that there is no common interface to run them, and the results are not provided in a common format. So we would like to have something that covers all this, just takes the RPM package and gives us all the results from all analyzers in some unified form.
Preferably as a service. I mean it would be really fun to fix those stuff if there was some metric for a package and metric for the maintainer, how we fix this stuff, and wall of shame and stuff like this.
Maybe wall of success.
Yeah, but we actually need to start. Before that, we have to have a way to actually run the things and have a way to have a common understood format, because, like I say, there are a bunch of these tools. They're really cool, but all of them report in a whole bunch of different ways. So, bring it together to actually.
I think we have it. I will cover it later.
Cool.
But I completely agree with you. That's the second step, and we have it in our future plan.
Great.
So, do you have any more questions to the static analyzers themselves in Fedora?
I'm a little curious if you're happy with what kinds of problems the static analysis finds, or is it just this is what you have from the static analyzer, so it's good enough, or is
it's never good enough. We always need to improve the analyzers to get more precise results.
But it seems like you didn't raise that as something to be worked on, so is that just the domain?
I think both the major analyzers I had in the presentation are in active development.
Yeah.
So we are observing that in each next version we get more precise results,
Right.
and more kinds of bugs are covered by the new versions of those analyzers.
Okay, so you don't have specific concerns that you raise?
We have some, and we try to work on them.
Okay.
Both the analyzers are open source, so everybody can contribute. For example, if we know that such and such bug is not covered by static analysis yet, or the tools we use, and it is something easy to cover. For example, there was a request about signal handlers. There is some limited set of async signal safe functions in signal handlers that can be used in a signal handler. And if you use anything else, directly or indirectly, your software contains undefined behavior. So the idea was to implement a checker that checks exactly this, because we are not aware of any solution yet, and it is something easy to implement. So we are about to implement this as another pass to C-Lang or something. No? Any more questions to static analyzers? If not, I will go ahead to the tool we developed for running static analyzers. The tool is named CSMOG, and it's also in Fedora, so you can try it right now if you want. As you can see, it's very easy to use. You just give it the source RPM and a list of analyzers to use. The analyzers I spoke about are of course covered. So in this case, we can just say take this Kerberos source RPM and run it through CPP check and C-Lang and give us the results in some unified form. CSMOG is quite easy to install. You just install the package and add yourself to the group MOG. This is because it internally uses MOG, so MOG requires it, because it for some steps of the build it needs root privileges, So by adding yourself to group mock, it works for you even if you are unprivileged user. Here you can see how the results look like. We get, this is the HTML format. You can of course get it in the plain text form if you want, for example, to integrate this into your editor, so that you can go through the code and actually look for the suspicious places. In this case we have 4 defects. The list of course continues, but there is not enough space on this slide. You can see that one is from, 2 of them are from CLang, one is from CPP check, and the last one is from compiler. So for all these tools we get it in the same format. We can also see that one defect was detected by both CLang and CPP check. So it means that there is a higher probability that there is a real bug in the code, or at least that the code is not static analyzer friendly. So it's a good candidate for a rewrite. So that's the format we use. We have some tools for processing this format. We can compute differences, we can filter defects by various criteria, by checkers, paths, and so on. So it is once we get this for the package, it is the results are really easy to work with using this. Do you have any questions?
As far as the format goes, this is actually an RFE. Could you possibly output tap?
That?
Yes.
That's some format?
Yes. And
I'm not aware of it.
it's the same thing protocol.
Mm-hmm.
And that would make it easier if we wanted to make this a taskicon task in the future.
Yes, that's also in our future plan to integrate it into taskicon.
So,
but the format is for the results of tests?
yes.
I'm not sure if it can be easily mapped. I would need to look at the format and check whether it supports all we need. But all the tools for processing the results already support 3 different formats. So it is quite easy to add any other if it supports all that we need to express. Thanks for the comment. So what else can we do with CSMOG? As it could be seen in the results, it captures GCC warning if we ask for it. What is more interesting is that it can change the GCC warning level. So if we have package that produces no warnings during build, we can increase the level and find some issues that were hidden before. This is fully transparently to the build process, so it works independently of the build system that the package uses. It doesn't care if there is CMake auto tools. Even if the package overrides the RPM defaults, we are still able to set the warning flags for the package. We can also check for downstream only bugs. So if we know that the package is regularly analyzed by upstream developers and they fix everything that is worth to fix and the rest is false positives, we can just check our downstream patches for the bugs. So in this case we usually don't need to go through hundreds of bugs and just look at the 4 possible bugs, for example, in our downstream patches. We can analyze also upstream tarballs instead of source RPMs. we just say which build dependencies we need to install and what what command we use to build the package. And then it works similarly as the source RPM variant. We get the results in a predictable amount of time, which is implemented by a timeout per compilation unit. So we can say that we give CPP check only 30 seconds and not more. So then there is an upper bound given by the time span, by the time limit, and the number of compilation units in our package. We can of course change the timeout, we can change the number of jobs we use for the build. So we can get less results in shorter time or more results in longer time. And what is also important, we are able to write plugins. So all the tools, GCC, CPP check and CLang are hooked into CSMod by plugins, and it is easy to write additional plugin for supporting additional static analysis tool. Here is something about the implementation of CSMod. As I mentioned before, it uses mod, which is a change root based tool for building RPM packages. We use it for building production packages, so the environment is quite close to what we use in production, and it also makes it easier to do destructive changes in the change root. We can, for example, simplify system headers if the static analysis tool is not able to compile them. It would not be possible on our live file system, but the change root is used for one scan anyway, so we can do whatever we need. And besides mod, it also uses CS-wrap, which is a compiler wrapper that can capture its output. If we build in parallel, it of course needs to synchronize the writes into the capture file. It can implement the timeout. So we've read both the compiler and the static analyzers to capture the timeout, capture the diagnostic output to set the timeout for one job. And it is also responsible for adding or removing the compilation flag as we need. And what I forgot to say that it translates the relative path to absolute path. So if GCC returns us some base name in the diagnostic message, we automatically translate it to the absolute path, because at the time we know the current directory. It would be lost if we didn't do it. As I said, we have some tools for processing the results in the formats we support. It is the CSDiff utility, which acts like diff utility, but for the formats we support. So we can either get the list of defects introduced in the new version of a package, or we can get the list of fixed defects in the new version of a package. It can be also used for filtering false positives, because they can be placed in some text file that saying that we know these bugs are false positives, and we can just subtract them from the results we get. There is also the CS-grep utility, which can filter the list of defects by various criteria, and the CS-HTML utility that produces the HTML report. That's the only format we use as output only, because it's not something that we can operate on easily. CSDiff is also a new package in Fedora, so you can easily install it and write some scripts using this tool. Do you have a question?
You say we see a stiff matches defects introduced by an update. That means all the new defects?
Yes, that's the defects that were not present in the stable version, and we are introducing them in the updated version of the package.
I guess I'm just curious about one question. So often when code changes, bits move around. So how do you tell an old defect that's moved down 30 lines from an actually new defect?
The trick is that we don't check the line numbers.
Good, yeah.
Because usually the diagnostic message is enough unambiguous to identify the defect. So we just check file names, diagnostic messages, and not all of them, but the significant one. So there is some algorithm. It is we use it 3 years already, and it gives us quite good results now. So it's not something written from scratch. It's proven to be correct in most of the times. Sometimes if there are big changes of code, we can of course report something as a newly introduced bug, even if it's not. But I don't think there is some sound and complete algorithm that would decide it for any program. So there are some mistakes in the output, but they are very rare in our experience.
The benefit of CSD is that you can also see not only new introduced warnings, but also the fixed warnings, so you can compare them.
Yes, and if something appears in both fixed and newly introduced, it's candidate for mismatched defect by this utility. So our future plans include writing plugins for additional static analyzers to support additional programming languages like Python or Java, and as you already suggested, to expose CSMOC as a service. We can, for example, hook a task on taskotron, but I don't think that's something that should be implemented in CSMOC itself. It should be really used just as a tool to analyze packages, and the service can be built on top of that. As an example, you can take mock, which is used for building packages, and it's used by the Koji service to actually provide this as a service.
So some time back we analyzed all Fedora binary packages to figure out if certain compile time flags were introduced, like whether it was PI enabled or it had a well go and things like that. So is there a plan to analyze all existing source RPMs and probably find bugs?
You mean to go package by package? Yes, we have done it regularly for each major Fedora release, but we didn't file any bugs. So we just provided maintainers with the results and asked them to look at it. In some cases it is difficult because there is a lot of bugs.
Yeah.
So if the maintainer sees thousands of defects, they just give up.
Yeah.
I think what makes more sense is to just check the updates and make sure that we are not introducing new bugs in the update. We do something like that for enterprise Linux packages,
Exactly.
and I think it would make sense also for Fedora.
So that's what leads to my second question. Would it make sense to integrate this with Bodhi? Like when you submit an update in Bodhi, it probably runs a static analyzer in the backend, and there's a link where the package maintainer needs to click on Bodhi interface itself to have a look at all the new bugs probably which they introduced.
It makes perfect sense.
Yeah.
But we just need to build a service,
And
open source service.
That's where Chaskotron would come in.
Yes, we are looking forward to cooperate with Taskotron group and get this integrated somehow.
Well, also in Red Hat we have this CSMOC as a service, and there is also a tool hooked on this, so you can verify each defect and say, yeah, this is a bug, or no, this is not a bug, and it will remember your decision, and in the next update it will remember, okay, the maintainer already said this is not a bug, so I will not show this defect again. So yeah, this tool is already in Red Hat, but it's not mature enough or to bring to Fedora yet, but this is our future plan to make it available in Fedora too.
Actually, the main reason is not the maturity, but the connection to Coverity, because we use Coverity in Red Hat internally, and we cannot provide access to the other guys. So we have to get rid of the Coverity to make it more open, to make it more usable.
Well, not just that, it's just actually hooked directly onto our release tool. So yeah, we have to support like different backend, which is like fed message and body.
And Tomáš is the main developer of this infrastructure, so it's up to him to get it open sourced and available.
Another question for Taskotron might be the resources, because the static analysis is quite expensive. You may need the machines with like 8 gigs of RAM, and it takes some time, and it cannot be run during the build time because it sometimes modifies the build route, so you have to run it separately. So yeah, the resources are another question for the Taskotron and running for every single Koji build.
Yeah, I think that's one of those things that it's a use case that we had in mind when we started Taskotron. Let's start the conversation. I don't know enough about static analysis. It was just something I was interested in doing, so I'd be picking other people's brains on what makes sense, whether it can work. But I suspect that's probably a better conversation for not in front of everyone.
Yeah,
right now.
We can discuss that later on.
Yep.
So, as a follow-up to what you were saying, so you plan to support a way of filtering out what might be considered false positives or things that the developer just wants to ignore, warnings that they just don't want to see anymore.
Yeah.
Is that language specific, or would it essentially work with all these postulated plugins?
Yes, it works exactly with all the plugins because they use the same format. We have JSON format, and it looks at all the defects, and that's the advantage, that we have common format and we use it, and it's directly hooked into it. So as John was saying about the tab format, we would have to like make a converter or something like that, so it would understand the new format and it would know how to figure it out. So
That's why I was asking about the tab, because Taskotron understands tab.
Yeah. John, that's not the way we want to do it.
Okay.
So, I just have a comment. So, so I work with the installer team and we run Pylon, which is kind of a standard static analysis tool for Python.
Pylon?
Yeah. And so basically what I wanted to do was something similar to your diff, because we had a ton of Pylon errors and we wanted to kill them gradually. So we would want to say, well, how many new ones does your commit introduce? So we wanted a diff of commits. And so actually I asked around on various channels, and there wasn't anything like that. And the consensus was that it would be very hard to do. And the best that people could do was say, well, on the lines of code that your commit has touched, is there now a warning? Which is a completely different idea. Somewhat useful, but as you can see, possibly not as useful as saying, what new errors has your commit introduced?
But the commit can remove some warning and introduce another warning.
Yeah.
So you need to check that the warning is really the same as before.
Right, and the consensus among the Pylon community was that that wasn't there, and that was very So I don't know what to,
I have heard of Pilot, but I haven't yet looked at what output format it uses. So I need to look at the output format, check how it can be converted to the format we use.
yeah.
And then it's quite easy to run CSD on these results.
Well, I think that what you may find is that the errors is that you're getting somehow very cooperative errors with CPP check. Or errors that cooperate with your method of getting the difference, and that it probably will be not so good with Pilot. That's my guess, based on the...
For example, if you look at the format, CPP check also gives us just one line.
Yeah.
It says the error is at line 166 in this file, and it gives us ID of the checker that found the error,
Right.
and the diagnostic message. That's everything we get. And if we just compare this string and the file name, we are able to match the defects. We just ignore the line numbers and it works quite well.
Yeah, I suspect, based on my experience with 1400 Pilot errors, that there's too much slop in the Pilot output, but it's not worth talking about anymore.
But even if it's fuzzy, it also helps. Yeah, so you don't rely on this diff completely, but you just use it as a base and just check, look around, and then you have some number of wrong defects in this list, in this diffs, but still it helps, even if it's not reliable as it should be.
Yeah, for example, for client, there was no such differ before the CSD, and we thought it will be hard, and it matches quite well. So I guess for the pilot, I have seen the output, and it shouldn't be a big problem. Because if you add some defect, which will match some older defect, you will remove just one, and you will have the new one added. So if you had like the same defect with the similar things before, and new one gets added, you will just remove one of them. So we'll still see the one more defect in the comparison.
Well, I wish you luck.
Thanks.
Well, regarding this filtering of false positives and matching the diffs, but I was thinking if this would be better to implement on the task control level, because all these changes, all these tests can be, or I think it would make sense to be able to mark some of the changes to be false positives, but well, generally not only in the static analysis. So maybe
You mean you need to keep the data about those false positives somewhere, and probably with task control is the best way to keep the state of a package and to store the data about the errors, because you don't keep it inside the SRT. You don't, when you run CSMOC, you don't want to keep the data about errors inside the tools you use. You want some external storage.
The whole technical details, okay. The stuff we already have is great, but I believe that the hard part is motivating maintainers and developers to do the stuff.
Definitely the most difficult
So
part.
we need to integrate with social networks and give them
But
badges.
giving them the technical equipment is also motivation. Because if you, for example, need to eliminate GCC warnings, and there is no easy way to capture them, to compare them, and so on, then it's difficult job. If you have this equipment, I think it makes the work more attractive.
And also about static analyzers, there are language-specific analyzers, but do we have some RPM-specific analyzers?
You mean for the spec file?
I don't know.
There is the Fedora review script, but
There are two that I'm aware of. There's RPMlint and RPMGrill. RPMGrill will also run RPMlint. RPMlint looks at the spec file for things like making sure the license file is correct, making sure that you don't have what it considers spelling errors. RPMGrill goes into a bit more detail, actually runs files through antivirus and a few other things. So there are some existing tools, if that's what you're looking for.
Yeah.
Okay.
I'd like to ask about the C-Lang analyzer. Is there any way how to shut the warnings up? I mean, if the analyzer gives a warning, I analyze the code, I see that this is false positive, and I want to suppress the warning in the next run.
I think it is possible to turn off the checker, so that it does not consume resources if you don't need it anyway.
Yes, but I mean, if I want new warnings, but I don't want the old that are analyzed. I mean, for example, I could put a comment on a line that would shut the warning up.
Yes, inline annotations are possible. I'm not sure about C-Lang, but I believe they are. And they are possible also for CPP check and other tools.
Yes.
The problem is that for each static analysis tools, the format is different.
Yeah.
So if there is some code that triggers warning in many static analyzers, you need to have annotations for each of them.
Yeah.
So then it's better to just rewrite the code so that it does not provoke the analyzers.
But if you look only at the difference, you will not have to walk through the defects again, because it will be only once.
Well, the line numbers change.
Line numbers are not the big deal. We are able to deal with them.
For example, here I see auto warnings, so I would like to.
So you have tried the CSMOC already and CSD. Try to compare the results, and you will see they will disappear.
Yeah.
We are quite sure because we use Clamp even in the RHEL packages, and usually all the defects are matched quite well, even if there is some. In the case of rebases, it has some duplicates, but in the case of common updates, when something just line changes, it's just fine. Yeah.
So to conclude, sorry, there's one more question. Go ahead.
Oh, I was going to say, you said that if you make the warnings into errors and force the maintainers to fix them, then you introduce more bugs. Aren't you going to make things even worse with all of these? If you want people to fix all these errors? It's kind of
we don't force them to fix it. If they don't fix the bugs we report, they are still able to build the package. That's the difference. We are not forcing them, we are giving them the data. So that it should be their decision to fix it or not.
But you should still use negative karma for the packages, right? So we will know that they are bad guys.
Maybe. One more question?
Just to veer off the conversational branch for a second. Do you know of Sonar? Which is
of what?
Do you know of Sonar, a project called Sonar?
Not yet, probably.
Okay, so it's like a. I was reminded of it when you were talking about the software as a service dashboard, or software license as a service dashboard type stuff, which Sonar does, but specifically for Java, so it runs find bugs and that sort of thing. And you get a really neat kind of dashboard with statistics on.
So there's a service for processing these results.
Yeah.
If I understand it correctly.
Yeah, and like we have it to Eclipse.org and like a whole bunch of projects that fed into it, and we get,
There is definitely more of them. For example, some people like to integrate this into Jenkins or some continuous integration testing framework.
Yeah, so it like happens after build jobs. So we get the static analysis is run, the build happens, which happens every time when it happens. So it's pretty well integrated. I just wondered if you'd seen it in action and it might.
Yeah, but this is for the upstreams usually because it's not on distribution level. This kind of project you have, for example, scancoverity.com. Every C and C++ project can join it, and you will get coverage reports for free. But of course, I'm behind some login or something. But it's only for upstreams, and if you look at Fedora, we have quite a lot of patches, downstream patches, sometimes backports or whatever. So you will not get these covered, and from my experience, quite a lot of defects come from the backports.
Sure, I just mention it as like a potential source of inspiration. But
okay, so thanks for the question.
Okay.
I think we are running out of time, so thanks for the discussion and enjoy your lunch.